One goal of software design principles is to help us create a system that is flexible, reusable, and maintainable. One of these principles is called separation of concerns. So what is a concern? A concern is a very general notion. Basically, it is anything that matters in providing a solution to a problem. Let's think of a supermarket. The concerns in the supermarket could be, how do I butcher meat? How do I bake bread? How do I accept payment? And how do I stock the shelves? These concerns matter when running the business to serve their customers. But what do you notice in how a supermarket is organized to deal with these concerns? There are separate departments that focus on each concern. Each concern poses unique subproblems, and each department knows what to do and how to address their specific concerns. The organization of a supermarket applies separation of concerns. A software system solves a problem in a similar fashion. The problem might be complex with a large number of concerns, or it might be simple with a small number of concerns. There are concepts that can be abstracted from the problem space. How these abstractions are implemented in the software can lead to more concerns. Some of these concerns may involve what information the implementation represents, what it manipulates, and what gets presented at the end. It's easy to get lost and tangled up in all these concerns and their subproblems. We need to be organized so that we can think about and address these concerns effectively. As the software solution is designed and constructed, we express how we can address the different subproblems by separating them into separate sections. You might have noticed that separation of concerns is a key idea that applies throughout object-oriented modeling and programming. The concerns that matter are addressed separately when applying the design principles of abstraction, encapsulation, decomposition, and generalization. Each concept in the problem space leads to a separate abstraction with its own relevant attributes and behaviors. These attributes and behaviors are encapsulated into their own section of code called a class. The view of a class by the rest of the system and its implementation are separated, so that the details of implementation can change while the view through an interface can stay the same. A whole class can also be decomposed into multiple classes. We may recognize commonalities among classes, which are then separated and generalized into a superclass. Separation of concerns is an ongoing process throughout the design process. Let's look at the behavior of a dog. Some basic behaviors that a dog can do are walking, running, speaking, and eating. While these behaviors are easy to identify and abstract, we need to ask ourselves which behaviors can the dog do all on its own, and which ones need help from something or someone else. If we examine the eating behavior more closely, we might come up with something like this. Our UML tells us that the dog has food, which it knows how to eat. We can tell the dog to eat food by giving it food, but is this the correct way of modeling the situation? Who is actually giving the dog the food? Does a dog always have food to eat, or is a dog given food to eat by an owner? In reality, a dog would need an owner to feed it. The dog knows how to eat food, but it doesn't know anything about the food it's eating until its owner feeds it. We need to separate two concerns, the action of eating and the action of providing food. This can be done by introducing a dog owner class. In our new design, the dog class only knows how to eat food. The dog owner class is the one that knows how to get the dog food and how to give it to the dog. We have removed the concern of how to get food away from the dog and let the dog owner handle that issue. In using separation of concerns here, we should only be encapsulating behaviors and attributes within classes that are concerned with the said behaviors and attributes. This helps us to create a modular system where individual classes can easily be swapped in and out without having to rewrite a large portion of our code. Let's illustrate separation of concerns with another example. Think about all the different behaviors that a smartphone is capable of. You can use it to take photos, schedule meetings, send and receive email, browse the internet, send SMS, or, of course, make phone calls. If we were to design a smartphone, what would the classes look like? Given the complexity of a smartphone, let's just look at the camera and the traditional phone functions. In this snippet of code, the smartphone class has attributes called camera and phone, along with all of the associated behaviors. However, there is low cohesion in the smartphone class because we have behaviors that are not related to each other. The camera behaviors do not need to be encapsulated with the behaviors of the phone in order for the camera to do its job. Furthermore, our smartphone components do not offer us any modularity. We cannot access the camera or the phone separately if we were to build another system that required only one or the other. We cannot replace our current camera with a different camera, or replace it with a completely different object, without removing the code for the camera completely in this class. So what changes can we make to our smartphone class in order to make it more cohesive and give each component of our smartphone distinctive functionalities? Well, let's check what our smartphone class is concerned about and separate them out. Our smartphone class has two concerns. 1. Act as a traditional telephone, and 2. Be able to use the built-in camera to take pictures. Now that we have identified these two different concerns, we can separate them out into their own more cohesive classes and encapsulate all the details about each into functionally distinct and independent classes. The smartphone class will reference instances of our newly created classes, so that the smartphone can act as a coordinator of the camera and the phone. This will let our smartphone provide access to all the behaviors of the camera and the phone, without having to know how each component behaves. Let's now take a look at what our new smartphone design looks like after we applied separation of concerns. First, we will extract the attributes and behaviors of both the camera and traditional phone into two separate interfaces. Then, we can implement these interfaces correspondingly with a first-gen camera class and a traditional phone class. Here is what the code looks like. As you can see, we have separated the camera and phone functionalities into different classes, each of which implements a certain interface. Next, let's redesign the code for our smartphone class so that it refers to instances of the camera and phone classes. This allows our smartphone to provide the functions of both the camera and the phone, while keeping the functionalities of either one separate and hidden from each other. The camera and phone know nothing about the other, but are still composed by the smartphone class. Also, we can have a smartphone constructor with camera and phone as parameters. Then we can create a new instance of the smartphone class by passing in instances of classes that implemented the camera and phone interfaces. Note that we leave it as a separate responsibility of who will instantiate the appropriate phone and camera objects. The smartphone class does not actually need to know. Finally, the smartphone class has methods that forward the responsibilities of using the camera and phone to these objects. Are you able to see how we now have a more modular design for our phone? If we want to swap out our camera or phone classes for something else, we do not need to touch any of the smartphone class's code. We simply just change the code to instantiate the smartphone and its parts. The smartphone class is now more cohesive. The trade-off is that we have increased coupling in our system, because the smartphone class needs to know about the camera and phone interfaces and is indirectly dependent on other classes. We use separation of concerns throughout this example by separating out the general notions of camera and phone through applying generalization and defining two interfaces, separating out the functionality for a first-gen camera and traditional phone by applying abstraction and encapsulation and defining two implementing classes, and finally, by applying decomposition to the smartphone so the constituent parts are separated from the whole. Now that we've talked about separation of concerns and completed an example, let's take a quick quiz to help you gauge your understanding of how separation of concerns works to meet our design goals. Our goal is to create flexible, reusable, and maintainable code. Separation of concerns creates more cohesive classes using abstraction, encapsulation, decomposition, and generalization. This creates a system that is easier to maintain because each class is organized so that it only contains the code that it needs to do its job. Modularity is increased in turn, which allows developers to reuse and build up individual classes without affecting others. In our smartphone example, it is clear where the boundaries of each class are. However, real-world problems may not be so obvious. Deciding how to abstract, encapsulate, decompose, and generalize to address the many concerns for a given problem is at the core of designing modular software.